Welcome to the Chorus One podcast. In this podcast, we explore the emerging open financial system facilitated by scalable, interoperable blockchain networks. Tune in every Monday to dive deep into cutting-edge projects and protocols with Chorus One team members and guests.
So welcome to the Chorus podcast. Today we have an amazing recording for you. I am conversing with Kevin Seqniki, who is one of the co-founders of AVA Labs. They're working on a consensus protocol called Avalanche, which has really some revolutionary properties. Kevin, welcome to the show.
Thank you. Glad to be here.
So you're working right now on AVA Labs. It's a company that's also co-founded by Emin Gunsirer, who is a professor at Cornell. And I'm just curious about your story, Kevin, and how you came to found AVA Labs and work on this interesting consensus protocol called Avalanche.
Sure. I've been in crypto for many years, so let me roll back the clock a little bit. I first got into crypto, I think, a few months after the white paper initially came out, and I was a lurker for a long time. I was still early on in my career, so I didn't quite understand the technology for quite a bit of time. But then I went to college and I got involved into cryptography, did research there, did some stuff in fully homework encryption. So, I got to understand what Bitcoin really was from a technological perspective. And so I became really fascinated about the notion of decentralized finance, decentralized computation. And then I decided to continue studies in cryptocurrencies in general and distributed systems in my PhD at Cornell. So the Avalanche project is something we've been working on for some time. And it's really coming from a desire to reimagine the entire tech stack of how you build consensus protocols. And there is this fantastic literature of epidemic-style protocols that makes usage of these really great properties of small subnetworks and how they can drive consensus to larger scale systems from just local statistical snapshots. And that basic idea is what sort of drives the whole consensus protocol of Avalanche. So it's an interesting and I would say pretty novel method of building consensus. And so that's what we're building with AVA.
So last year when I was actually trying to learn Go, I was shopping around for a project to build in Golang. And the Avalanche paper had just come out.
Yeah.
So I actually built a simulation of not the final protocol, but the basic protocol. And so my understanding of this protocol is, I think, quite good because I have actually done this simulation.
Right.
But like any protocol, there's a bunch of nodes that are trying to come to consensus over some data set. So give us an overview of how consensus happens in Avalanche.
Yeah, so let me maybe take a stab at that by briefly describing how we would come to consensus in a classical protocol. When I say classical, I mean really a voting-based protocol that requires all-to-all voting and provides you with deterministic guarantees of safety. So, once we reach some certain set of properties, then I know for sure that consensus has been reached and there's no reverting back. So in a classical protocol, you have a set of end nodes, and the basic operation is that we must all reach some desired agreement, some threshold level of agreement among some large supermajority of the nodes. And once that threshold agreement is reached, precisely, some threshold T, then there is no other possible new subset of nodes in the network that can possibly agree on a different value. Now, this is the basic construction that provides safety in classical protocols. It's what comes from, set theory, basically.
So stated in different terms, in a protocol like Cosmos, since many of our viewers are coming from Cosmos background.
Yeah.
The nodes are the validators. And in Cosmos, like nodes with 66% of the voting power, that's the threshold you're referring to.
That's exactly right.
If they agree by signing off votes for a particular data set and if they consist of 66% of the state, that is the threshold. And that is when something is approved and then that thing cannot be reversed.
Exactly right. That's what I'll call the quorum intersection property. And that threshold is not a magical threshold necessarily. It just turns out to be the threshold that is required when you do have up to 1/3 Byzantine nodes, which can split the network in half and so on. So that threshold is parametrizable, but that's a fundamental threshold when you do parametrize your system for 1/3 Byzantine nodes. So once you reach 66% or 67% rather, then you have no other way to construct any other larger subset of nodes that reach another different agreement. But in a classical protocol, a lot of work goes into really how do we get to the 67%. So this is a nice property with 67% and we're stuck there. There's no reverting back. but there's still no description on how to get there. So a lot of protocols have come over literally decades trying to optimize precisely that operation. We select a leader typically, almost every single case that I know of in classical protocols, elect a leader in order to facilitate this procedure. The leader may be Byzantine, in which case many different protocols have come along that specify different methods to replace the leader such that we reduce the message overhead and so on. So, Tendermint has its own variant. There is the hot stuff paper that has its own variant. PBFT has its own variant. Every one of these classical protocols has its own variant of leader election. So the nice thing about classical is that it provides a guarantee 1 of safety. Once you do reach that threshold of 67%, then you are guaranteed, set theoretically, there's nothing else that can happen. But what happens if, you potentially reduce that requirement? You say, look, I don't need a probability 1 guarantee of safety. Instead, can we construct new protocols, voting-based protocols, that have different properties, assuming that I relax my requirement of probability 1 guarantee of safety? Maybe probability 1 minus epsilon, where epsilon is parametrizable. And it turns out that if you relax this requirement, a lot of protocols get to be much more efficient. We've seen this in randomized protocols. We see this, for example, all the time in complexity theory when you're trying to solve for algorithms where instead of getting a perfect answer, which might be, NP hard, whatever it may be, instead you want a mostly correct answer, 99.99% correct answer, but that answer is significantly more efficient because it uses some randomization. So this is a well-known class in complexity theory, and it's been well known for decades that if you just allow a little bit of error, then your protocols, your solutions get significantly more efficient. And so that's the same guiding principle in Avalanche. It's inspired by the idea that instead of requiring all-to-all voting, we just use statistical snapshots. So I only select a few other nodes in the entire universe of nodes and sample them repeatedly based on some value. So what this gives you is significantly higher scalability. In fact, turns out that the scalability is nearly independent. When I say nearly independent, I mean the message complexity is nearly independent of the network side, which is a fantastic property to have. So it doesn't matter whether the network is 1,000 nodes or 10,000 nodes or 100,000 nodes, your message complexity per round is the same, which is a really fantastic property. And also additionally, what it provides you is that it gives you this inherent ability to reach consensus without ever necessarily using a leader. You can use a leader as an optimization, that's fine, but you don't require one. So this random subsampling drives the network towards one universal lowest energy state. So basically one proposal rather than multiple proposals. So this is a really nice tool set to have, and this is what we've been trying to build here.
I tend to imagine Avalanche of course, you gave the perfect technical explanation for it. I'm trying to relax the need for the technical explanation and give
of course,
a social explanation for Avalanche. And imagine we are all in this country where it's an oppressive government, right?
Yeah.
And we want to do a protest. Many people in many different universities, many different students in many different universities that want to do a protest.
Yes.
Protest is most effective when everybody shows at the same place at similar times. Otherwise, it isn't effective. So you see that there is some need for consensus.
Right.
The consensus here, the data here is
yes.
When do we go and protest and where? When and where is the thing that matters here.
Right, exactly.
And kind of the fundamental intuition of Avalanche is, so if I'm one of the prospective protesters, I call up maybe 10 other prospective protesters I know, and I ask them, hey, when are you guys going to protest? And I get replies from all of them. Now, when I get these replies, well, I see, some small majority, maybe 30 or 40% of these replies, they are saying, we are going to go to Tahrir Square on 4 p.m. on this date, and we are going to go and protest. And so when I get those replies, I also think, I'll also drop by Tahrir Square at that point in time, right? Because that was the majority in these 10 people I knew, I called up. Now, other people are doing the same thing. So there's some other random person, they're also dialing to 10 people, and I might be one of the 10 people they dial to. And when they dial to me, I reply to them, hey, I'm going to check out this at this place at this time, like 4 p.m. at Tahrir Square. And I communicate it to them.
Right.
And they do the similar thing. If they find some sort of small majority, then they also decide to go to that same place. And so all of the prospective protesters, they are doing the same thing. And initially, these protesters might end up agreeing on like different places and different times. But then over time, because they keep calling each other and keep changing as per the majority feedback they receive, all of these protesters slowly, after a lot of calls, end up aggregating to deciding to protest at the same place at the same time. And that's how consensus or coordination happens.
That's exactly right. So that simple process turns out to be sufficiently effective to reach agreement, surprisingly, in just actually logarithmic number of rounds. If you have, a binary decision, which might be, for example, hey, should we protest on Saturday or should we protest on Sunday? Like, these are the only two possible, because during the weekdays we're not going to protest. We're busy with work, but on the weekends we're going to protest. So do we do it on Saturday or on Sunday? And so if I just call up my friends and I see that, oh, okay, look, most of them are saying Saturday, so I'll stick with Saturday. Other people will ask me then, and I'll be like, well, look, I saw that most of my friends were saying Saturday, so I'm going to say Saturday too. And those guys are then going to repeatedly say Saturday, and there's this compounded effect where everybody now all of a sudden says Saturday. And it turns out that if you have some large threshold majority of people all saying Saturday, then it becomes really hard for us to switch to Sunday now. So we're stuck in that position, and you can say that, we're agreed on Saturday and there's no way for us to go on Sunday. Now, of course, it is still possible for somehow in some very crazy universe for us to go back into Sunday. It's just very unlikely. And this is where that 1 minus epsilon probability comes in.
Yeah. So basically, if the government has a bunch of agents and they're trying to infiltrate this process, these secret agents of the governments are trying to say Sunday every time when others are coming towards Saturday.
Yes.
They're trying to corrupt the process. The insight is once some kind of threshold start to agree on Saturday, these secret agents won't be able to have the results switch back to Sunday.
Exactly right. They would have to have significantly more. As more people agree on Saturday, they would have to have more and more representative votes in the network. So if you're trying to protest, then you don't need to have a very large WeChat group. Instead, you just have personal WeChat groups with your friends and just coordinate with this protocol and you will reach agreement.
That's the fascinating property of Avalanche, right? So just like I just need to dial to my few friends.
Exactly.
As a node, I just need to dial to, let's say, 10 or 20 other nodes, even though the total network might be 10,000 nodes.
Exactly.
I need to only dial 10 or 20. And I need to do like maybe 3 or 4 rounds of this dialing 10 or 20 nodes.
Exactly right.
As long as all of the nodes do the same thing, all of the nodes can achieve consensus over some data set.
Exactly right. Exactly right.
What strikes me as very remarkable about Avalanche in particular is when I built the simulation, of course, you can see graphically this epidemics spreading.
Yeah.
By background, like I'm a biologist, right? And
you'll see a lot of similarities then here. There's a lot of physical phenomena that are similar here.
Yeah. And like I was at this beautiful garden and then I could see this big school of fish that were swimming.
Yeah.
Now, the interesting thing is like when these groups of fish or these birds, they swim, they usually like go in the same direction.
Yeah.
So intrinsically, for them to go in the same direction, well, that is consensus, right? You need consensus to be happening for all of these agents to be swimming in the same direction. And if you start to think of it, like what is the intuition behind PBFT? The intuition behind PBFT is like, if this is a big group of birds, and one of the birds is a leader, and then one of the birds is going to squawk to the other birds, hey, let's go north.
Yep.
And then all of the other birds are going to vote. They're going to pre-vote first.
Exactly.
And then after pre-vote, every bird will hear what every other bird pre-voted. Then they will pre-commit. Yeah. They will again vote. And then they'll say, we agree with the leader, let's go north. And then when 66% have agreed, the whole flock goes north.
Exactly.
That's just not how it happens, right?
Exactly right.
There is no long-range communication in this flock of birds or flock of fish.
It's just local, exactly.
There's none at all, right? Probably the bird is looking only at its neighbors and the fish is looking only at its neighbors. And somehow there's still a way of doing decision making, right? Like some birds might fly one way and others copy it and others copy it, and then suddenly like it snowballs or it avalanches it into a change of direction.
Exactly right.
And avalanche, analogy wise, it seems to be very similar.
That's precisely right. Yes. There is no long range communication here. It's just based on your local observations of the system, you're able to make characterizations of the system as a whole. Of course, you may be wrong about this local observation, but repeat it sufficiently and observe it over a sufficiently long time, then it will be very accurate and it will be able to coordinate with very large number of other entities or whatever it may be with much higher efficiency.
So you mentioned that there was some kind of relaxation to safety that was needed, right? Like, so instead of some safety guarantee of 100% can never be reversed, that it needs to relax to 1 minus epsilon. What is this epsilon, and like what are the practical consequences of this epsilon in the Avalanche system?
Right. So that's a great question. The practical considerations are effectively negligible. This is really a consideration in the theory. So turns out, as I said, precise solutions to certain problems are well known to be NP hard. But their probabilistic solutions, they're close to perfect but not exactly perfect, are known to be very trivial to solve. Very large class of complexity problems follow this same pattern. For Avalanche, this epsilon, as long as it's non-zero, it's strictly higher than 0, so it's strictly less than 1, you can still make it practically close to 0, but it still has to be greater than 0. Then you still have all these really nice properties of scalability. So your computer, for example, actually can still miscompute. Your CPU, Intel, can still miscompute something and provide you with an erroneous answer. So every single laptop, every single computer out there computes the right output with probability 1 minus epsilon, where this epsilon is based on a very complicated set of external inputs and so on from the environment, like the CPU might be corrupted and so on and so on. But in the same way here, you can make this epsilon parametrizable in the system. So the nice thing about Avalanche is that while we do recommend you certain values to set up such that this epsilon becomes negligible, you can actually set it up for yourself. And there's a trade-off between latencies and your security guarantee. So the higher the latency, like in the same way that you would wait in Bitcoin, the higher the number of block generations on top of your last transaction, the higher the safety in Bitcoin. In the same way in Avalanche, the higher the latency that you wait for confirmations, like everybody says red, everybody says red, everybody says red multiple times, many times over and over again, then the higher this guarantee is. It never quite reaches 1. In fact, it only reaches 1 at infinity. So for infinite number of times, we have said red or protest on Saturday, then we're for sure guaranteed this outcome. But before infinite number of times, you still have very high security guarantee. So for example, in logarithmic number of rounds, under a sufficiently small Byzantine adversary, then you can parameterize your system to have security guarantee of 1 minus 2 to the minus 64. So basically probability 1. The same probability of being able to decrypt some key that's encrypted with 2 to the 64 bit encryption.
That's very interesting. So is it right to say that on top of Avalanche, you are building like the cryptocurrency and a blockchain system, and we'll get into the properties of that piece. But is it correct to say that your blockchain will have finality?
There is finality based on your local requirements. If you believe that your finality guarantees are sufficient with the 5 nines guarantee that's usually used in cloud computing, for example, then that is your finality. But let me put it this way. From a theoretical perspective, there is never quite any finality. From a practical perspective, absolutely. You just simply set up how willing you are to accept something with probability 1 as epsilon. Once you agree on what this epsilon is, you set your own local parameters, and now you get finality in Avalanche.
So exchange can set epsilon very low. Starbucks can set epsilon relatively higher because they're only selling coffee.
Exactly right. And they can get very quick confirmations for their coffee.
And of course, the attractive property is that the Avalanche network can have a large number of nodes, like 10,000, 20,000. They are all admissible.
Yes, exactly. The performance per round is independent of the number of nodes. The latencies increase logarithmically with the number of nodes, although you can amortize this. So the cost here is very low, but it turns out really like the bottleneck here becomes, is your computer able to go through hundreds of thousands or millions of connections? It's really more of a hardware limitation at that point than protocol limitation.
So in terms of like this system you're trying to build, the practical system you're trying to build, you will need to pick some parameters. Even though the consensus protocol could allow 1 million nodes, maybe in the practical system, you might only start with 1,000 with a certain amount of performance. What's the kind of system you're targeting? Number of nodes, the performance, the confirmation latency?
Really what we want to do is get to a point where there is not a single identifiable entity in the system that can control the network in any measurable way. That's what I would say is probably the most important criteria for decentralization. A raw number of nodes is certainly not a very good metric, but it's also not entirely independent from decentralization. Certainly if you're in the thousands of nodes and they're all distributed across the globe, then there is a pretty measurable and meaningful measure of decentralization there. But I would assume that if we get to the same levels of the number of single clients running on Bitcoin right now, which I think as of last time that I checked was 9,000, 10,000, then that's a measurably similar decentralization metric for us. So that's like a golden standard for us is 10,000 nodes or more.
Many of the other proof of stake algorithms are capped at 100, 150, 200 nodes.
Yeah.
Which is why Avalanche is in its own territory, right? Like in terms of the network size.
Yeah.
I'm also curious about, you mentioned that like these nodes, they can elect to have a leader, but they might not. Now, one of the other challenges with traditional proof of stake algorithms is there's usually a leader, and those systems work fine until you start to do decentralized like order book matchmaking based on a leader. Right. So if you have like an exchange that's running and there's a leader and the leader has to match, then of course the leader has a lot of power on like front running and those kinds of attacks.
Exactly.
So how can Avalanche work without a leader, and what is its consequence for these decentralized exchanges?
If you were to build, actually, let me take a step back for 1 second and sort of describe the architecture a little bit of the AVA platform. So the base layer, that's where all of the set of AVA validators are, and they're going to be operating on this DAG. So that base layer is going to never have a leader. Payments, checkpointing, staking, all these things are going to be happening there that are critical to the infrastructure we build on top. And I'll go into this in a little bit into something we call the FSS, which we call Feature-Specific Subnetworks. But the base layer will never have a leader. But let's suppose that, for example, you were to launch either a decentralized exchange on directly the AVA DAG or on a subnet within the AVA ecosystem. So on the first one, if you were to launch it on the AVA DAG, then you would have significantly less ability to try to, sway the transactions that are being accepted in the system. And the reason is because there is no leader in that architecture. Simply transactions are being issued, and using this repeated sampling, we almost randomly move towards one direction of conflicting transactions. So there is no leader here dictating on this next transaction will be exactly this one. It's really more of we'll decide as a crowd. If you were to instead issue a decentralized exchange on a subnetwork on AVA, then you have two options. Or actually you have multiple options. It's very open, very heterogeneous. So let me just say two. You can still keep it as the leaderless version and build maybe a linear chain directly on the subnetwork. Or you can also choose to build using a leader scheme. In that sense, in that case, you might want to consider more sophisticated technologies to potentially prevent from front running, like SGX. So something, and I'll certainly go into it when we talk about the platform itself, but something that we will be supporting is the ability to support SGX, Intel SGX. And it has been demonstrated that there is protocols that exist using SGX that allow you to build unfront-runnable and uncheatable decentralized exchanges. And so, you can certainly build something like that on the platform.
So that's very interesting. So in AVA, there's this base layer, which is one large network without a leader, consensus, and then you can have sub-networks of this base network.
Right. Exactly
and these sub-networks can service other needs.
Exactly right. Yeah. So let me go into this a little bit. So we call these as I said, FSS, it's a feature-specific subnetwork. So where is this coming from and what does it really mean? Well, in our sort of bet into where the crypto space is going, or rather in our vision of where we believe the financial ecosystem needs to be, is in this very unifying, almost like an operating system of finance, where you allow developers to come in, create their apps in their own specific language, in their own specific execution environment, and not really force down on them a particular architecture. And this has been, the latter version has been, unfortunately, the way we've built every single one of decentralized platforms up to now, including Ethereum, for example, being the most famous case. So all of these platforms are very monolithic. They implement one virtual machine, the EVM, for example, for Ethereum, one scripting language, which is the BTC script for Bitcoin, and so on. But if you want to build a unifying platform where you allow anybody to launch digital assets and other functionalities on this operating system of finance, let me call it that, then you really need to allow a large amount of flexibility for developers. So you need to allow developers several things. You need to allow developers the ability to set attributes. So they want to be able to label the kinds of functionalities that each of these subnetworks is capable of. So you want to be able to say that a particular subnetwork of my application will service, let's say, titles. So anybody validating on this subnetwork needs to be aware that these are special types of transactions that are very important to store for the long term. Developers also need flexibility in the kinds of virtual machines that they use, in the kinds of language that they write their applications in. So imagine, for example, if you implemented an operating system or you took Unix and you forced everybody that was writing applications on Unix or Mac, whatever, to only write in one language and nothing else, and there's no other possible thing for you to use. That would be disastrous for that platform. It really would never take off. So what we're building is the ability for any developer team to come in and launch these feature-specific subnetworks, which define their own virtual machines, their own scripting languages. We have this notion of a plugin almost. So you can launch this new type of subnetwork, and then you can simply wholesale import various different plugins, which can be the Ethereum virtual machine plugin. That's one functionality that you can import that gives you the Ethereum virtual machine. You can import, for example, SGX capabilities. That's another plugin within our system. And very importantly, what this also allows is something that's critically missing in crypto networks nowadays, which is compliance. We want to make sure that we build highly compliant networks for everybody that needs basically everybody needs compliance in a lot of ways. So you can have, for example, a financial institution actually launch assets and applications that have very strong KYC requirements, which is absolute must. So these are really powerful abilities that we allow for developers on our platform. And we believe this kind of architecture is really what creates truly what you would want to deliver to developers, an operating system of various different types of languages, various different types of capabilities for you to launch your applications in. And that's really how you create, I would say, a unifying experience within a crypto network. So that's our vision. We envision sort of global operating system of finance where all kinds of entities are building applications in a compliant manner, and they're issuing digital assets that represent all sorts of instruments. They can be, for example, crop insurance. It can be all sorts of things that are traded freely on this platform under the proper regulations.
That's very interesting. So if I were a developer building a feature-specific subnetwork,
yeah.
FSS, so I can choose like the low-level bytecode, of course, whether it's EVM bytecode, it's Wasm or something like that. Most developers don't care, but they can choose that thing.
Yeah.
And they can choose the higher-level languages in which they program. Could they also choose like the data structures and things like that?
Yes.
Which represent the ledger?
Absolutely. So for applications that don't require full total ordering, you can, for example, immediately just use a DAG. So an FSS within AVA would just be simply a sub-DAG of the main AVA DAG, and you would get significantly higher performance there. You could also choose to build a linear chain, which we fully support. We have a protocol called Snowman, which is a variant of Snowball that implements a linear chain. So yeah, it actually depends on your kinds of needs and flexibilities, what you want to build. Although the flexibility on WASM and EVM, that's important because different applications have already been written in various different languages that compile to specific virtual machines. And so if you don't support the ability for anybody to just come in and create a new plugin that represents now the EVM, and you don't get backwards compatibility, which would be a killer for the platform.
Okay. And so if I build an FSS, I have all of this flexibility. What assumptions do I need to subscribe to? So if I understand correctly, I need to subscribe to the assumption that my transactions will be done by the Avalanche network. So the capacity of this whole Avalanche network should be greater than the capacity I need. Is that right?
Right. So let me also maybe mention something that I believe I forgot to mention, which is the ability to label or provide certificates for a specific subset of the validators that will validate your FSS. So you have this specific subnetwork, which has its own data structure, its own bytecode, its own language, its own attributes, and its own validator set. So I can, for example, as an institution, I can come in and say, hey, I'm trying to launch titles. I want to make sure that I subscribe into potentially, this is an additional feature, you can choose to do it, into a legal contract with all of these validators that says that I'm going to, give you these data, we're going to launch this application, and I want to make sure that there is some legal backing to what we're doing. So the base AVA DAG, where the higher security system is, you can do several things with it, and you can choose as the creator of the subnetwork what you want to do with it. So you can choose to keep most of your data private outside of the entire validator set of AVA, and so most of the transactions stay within the FSS, and then every once in a while you maybe checkpoint things onto the main DAG. Or if you require very strong storage requirements and you do not necessarily trust the FSS validators and you want more guarantees, then what you can do is you can issue those transactions as well on the AVA DAG directly on the base layer and get the highest security guarantee, but of course the costs there might be higher. So you get to choose really what kind of trade-offs you want. I think you want to provide this general trade-off mechanism because I don't, as I said before we got into the conversation, that certain applications that require strong privacy and strong regulation on jurisdiction where this data is going, they potentially might only be executed on a specific set of validators and never touch beyond maybe a hash on the main AVA DAG. So that's the general flexibility we provide. Base layer, highest security guarantee, you can choose it, but you don't have to. You can move on to these more specific subnetworks which you have maybe legal contracts with the validators there.
So this base layer, the set of validators or nodes running the base layer, how are they picked?
Great question. So you can choose to pick them directly yourself. I can say, hey, I'm going to get Bob, Charlie, and Alice. These are my validators for my purple coin. And I'm going to give them a special certificate. So anybody else in the network, if you see this special certificate, then it was given by me. And those holders of that certificate, they are true validators of my purple coin. I can instead also create an open market. So I can say I have an application, which whatever represents purple coin again, orange coin rather in this case, and represents something else. And this application now, I don't necessarily want to specify the set of validators. Instead, I will allow anybody to become a validator as long as they maybe put up a stake or they choose some other conditions. They meet some other conditions. So it's very flexible in that regard as well.
Okay. So the base layer of AVA, if I want to become a validator for the base layer, not a feature-specific network.
Yes.
Then I need to have AVA tokens and I need to stake those AVA tokens.
Correct. That's for providing security of the system. Correct.
But once I'm a base layer validator, I could go to the Orange Coin network and say, oh, if I stake further Orange Coin, then I become a validator of Orange Coin network also.
Exactly right. Right.
Okay. So that way is like you can also have like this additive security. Each of these feature-specific networks.
Precisely right. But you must maintain the invariant that the base layer is always higher value than some of the components built on top of it. You want the base layer to really maintain this high security guarantee because a lot of applications will checkpoint into it. So they will require very high guarantees of the data that they're providing. And also for a base layer, that provides the basic universal method of exchange between the different subnetworks. So it's the mechanism by which we do swaps and atomic swaps.
What feels really interesting is you're using this term validators, but our nodes don't seem to be validators like Cosmos nodes. Because in Cosmos and other proof of stake systems, there's this element of delegation, which is here's a node and I as a user can delegate my stake to a node. Will AVA have something like that? Or as a user, I'm supposed to run my own node? If I have AVA, I'll run my own AVA node.
Certainly, you can, initially at the very least, you can delegate some of your stake in order to enter the system. So a key property that we want to ensure is that the stake amount is nearly minimal. It's just sufficiently large enough to prevent spam, basically. Somebody coming in and just creating thousands of connections for no reason. So just want to make sure that baseline is covered. But otherwise, it should be very trivial for anybody, simple people, on their laptop to be able to run an actual validator node, rather than other systems which may have $200,000. I believe Cosmos is about $200,000 to validate, I believe, for one. So that's nowhere near what we're trying to hit. We're trying to hit for a very small amount, and it just needs to be sufficiently high to prevent spam. And of course, the notion of validators, the base AVA DAG, where the checkpointing is done for a lot of chains, where the swaps are done, where the base payments are done. These are all replicated across the entire set of validators. But in our framework, in order to maintain the security invariant that, the base layer, this ecosystem is as secure as the sum of the components built on top of it, then you must make sure that before staking into any particular subnetwork, you first stake into AVA. Otherwise, you do not maintain that invariant. For example, you can enter into really weird scenarios where maybe Orange Coin, a subnetwork within AVA, that one is higher value than AVA itself. Then we don't get security guarantees. We don't get rather measurable security guarantees. I don't know exactly what the value of Orange Coin might be. It might be very valuable. But at the very least, if I have the invariant maintained, then I know precisely what the value is because I know what the base layer value is. So I always maintain that invariant. And in fact, if I create new coins and I see a new coin orange and I'm trying to maybe swap with it, I don't recognize that new coin orange. I don't know what its value is. So I don't know what my risk with swapping with it would be. But if I understand the value in respect to the stake on AVA, then I precisely know that the value of that orange coin is at least some percentage of the AVA tokens. So it's a direct measurable number for me to be able to say, okay, this orange coin has $2 million worth of security in it. It would be at least $2 million hard in order for somebody to take the system down. And so I'm pretty comfortable interacting and swapping with this subnetwork. So it's a very important invariant to maintain, actually.
We are running out of time, so maybe we could just cover sort of your current state and what's following in the next few months from the project.
Absolutely. We have been undergoing a private testnet. We have been doing testing on the payments platform layer. We're actually working right now on the GUI parts of the wallet. So we're going to be working on integrations very soon, and we're looking to do a public testnet by the end of September. That's been our goal, and we're looking to meet it. So once we go public testnet, the functionality on that public testnet will be the ability to launch, of course, do payments, but also launch these FSSs, do atomic swaps, support EVM at the very least. Optionally, would be great to have WASM support as well on day one, but it's not clear that we'll have it. By mainnet, we would like to have support for WASM, SGX, and a few other technologies. And additionally, really work hard on the user experience, which is very important, and for us to also build compelling applications on top. Mainnet, unclear when we're going to launch, but hopefully we're trying to target very, very soon after public testnet. We need to just, contingent on security audits and extensive testing going well.
Wow. So the main network could be in place in 2020.
Oh, yes, 2020 for sure.
2020 for sure. Wow. Now, of course, there'll be the AVA token in the system. So do you have any plans for the AVA token firmed up in terms of token supply, how it's distributed, etc.?
In principle, while distributed and in the hands of, it has to be as little concentrated as possible. Like nobody should be able to control the system. Nobody should have any sort of say here or manipulate it in any way whatsoever. Of course, getting to that point, it's a matter of a lot of complex operations, and it's really almost a social problem as well as it is logistical problem. So beyond that general principle of us making sure that nobody gets to control the system, not even us, of course, much less us, in fact, beyond that principle, nothing has been finalized on the token dynamics or anything like that. But of course, we're actively considering a lot of options.
Okay, so there may be an ICO, but it's not certain.
It's not certain, right?
Cool. It was great to chat with you, Kevin.
Oh, pleasure mine.
I hope our listeners, you got some idea of the AVA platform. Of course, I'll invite Kevin over again when it's like post-public testnet launch to discuss some of the other deeper features of the Avalanche system.
Absolutely. Thank you so much. It was great being here.
Thank you for listening to the Chorus One podcast. Visit chorus.one for more information about our work. Don't forget to subscribe to the podcast to stay tuned on new episodes airing every Monday.